So the next video in this series is on the matrix for the linear transformation. So it turns out that pretty much any linear transformation can be um, represented utilizing a matrix if we utilize the matrix in particular ways. Like, for example, when we're talking about polynomials and the way that we could transform polynomials into vectors, well, if you could transform a polynomial into a vector, then you could transform a polynomial or a set of polynomials into a matrix made up of a bunch of vectors. And so consequently, um, I, that's what we're going to be kind of looking at, and we're going to be talking about. We're going to be primarily using these a lot inside of chapter 6. Okay, so let's first talk about a matrix transformation. So a matrix transformation is a linear transformation from Rm to Rn. Okay, the matrix of the transformation is m by n. Is m by n. Okay, let's look at y. So let's consider A here to be this linear transformation. We already know it's linear. We proved that inside of the last video. So A will let it equal, right, 2, 3, negative 5, 0, 1, negative 1, 3, negative 4. Okay? And what we're going to say is that A is a linear transformation, and it goes from R excuse me, this should be Rn to Rm. And then it's going to go from R2 on to R4. Okay, the reason why is because what I'm going to do, my input vectors, if you think about this like a function, are going to be x1, x2, right? By matrix multiplication, I'm going to have 2x1 times 1x2. That's what are going to be my inputs. And then my outputs are going to be in R4. They're going to be x1, x2, x3, x4. We're going to end up with 4 values there. So my mapping is going to look like this. Right? My domain is R2, my codomain is R4, okay? And then we have X1, X2, X3, X4 over here, okay? That's kind of how this matrix transformation works. And as we said before, we know it's linear, right? All we want to do is we really want to start to define our codomain and our domain. So the number of columns is going to define the domain, the codomain, excuse me, and the number of rows is going to define our codomain, and the number codomain and the number of columns is going to define our domain. And the reason why just has to do with matrix multiplication. That's it. All right. Okay. Okay, so let's talk about a couple of basically a couple of theorems or yeah, theorems. We'll call them theorems. The first one is how do we generate a matrix transformation? So if E1, E2, E3, so on and so on and so forth, up to En are the standard basis for Rn. then the matrix transformation T is defined as A equal to T of E1, T of E2, dot, 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 all the T of En. So what is this saying? This is basically saying the matrix transformation is made up of what happens to the standard basis under the transformation. And what that means is also, if I can find the transformation of the standard basis by T, then I can find the matrix of the transformation. The standard basis by T, then I can find the matrix of the transformation. So let's consider an example. Let's suppose a race at 8:23. So let's suppose that I have T of x1, x2, x3. And that's going to equal negative x1 plus x3, x3, negative 2x3, 2x1 plus 5x2, minus 9x3, and negative 7x1 plus 5x2. What I can do is I'll rewrite this now. I'm going to rewrite this as x1, x2, x3. Okay. And then this is going to end up equaling x1 times 1, 0, 0 plus x2 times 0, 1, 0 plus x3 times 0, 0, 1. So there's my standard basis. Those are my standard basis vectors. And this will then equal, and what we're going to do now is I'm going to rewrite this whole thing, right? Okay, it's going to be negative x1 plus 3x3. Okay, negative 2x3, 2x1 plus 5x2 minus 9x3, and negative 7x1 plus 5x2. Okay, now if I rewrite, I've got x1, and x1, we've got the negative 1 in front of the x1 in the first term. There's no x1s in the second term. There's 2, right, in front of the x1, and negative 7 in front of the x1 in the third term. Plus, then we'll have x2, and there's no x2s in the first term, so that's 0. No x terms in the second term, 0. 5 in the third term, and 5 in the fourth term. Plus, and then x3 will give us 3 in the first term, negative 2 in the second term, negative 9 in the third term, and 0 in the fourth term. So what that tells me then, so basically what I've done is I've just transformed this guy, right, okay, or this one into this one, and I've transformed it into vectors, okay? So t of my standard basis vector 1, 0, 0 plus will equal -1, 0, 2, -7. T of 0, 0, 1, or 0, 1, 0, excuse me, 0, 1, 0, that's my x2 term, will equal 0, 0, 5, 5. And t of 0, 0, 1 will then equal 3, -2, -9, 0. All I need to do now, these three are now the three vectors of the matrix transformation. So t, which goes from R3 to R4. Okay, R3 to R4. How do I know? Because the standard basis vectors are in R3, and we transform them into vectors in R4. So it's going to go from R3 to R4. And how is it going to do it? It's going to be defined by the matrix transformation A, which will equal -1, 0, 2, -7. Excuse me. 0, 0, 5, 5. 3, -2, -9, 0. And that's my matrix transformation. How do I find it? Well, I had to transform my transformation, okay? And I treated these x1, x2, and x3 as scalars, right? But you can see how they would kind of represent the standard basis right here, x1, x2, x3. Those are the standard basis, right? Take those values. And then I just need to transform my new transformed values, okay, into vectors, associate them with the standard basis vectors, right, and then combine them all to make the matrix of the transformation. And that's how we utilize, like, the idea of this right here is the standard basis vectors being turned into the vectors of the transformation, okay, and this is how we go in and interpret vectors. Interpret transformations into vectors. Okay, great. I hope that helps. That is the matrix of the transformation. We'll do a little bit more work on these in just a little bit.